Deal. I'll go ahead and get started then. It's a minute or so after 2. I'd like to welcome everyone to today's edition of Keller North America webinar series. My name is Jim Husson. I'm a director with Keller North America and the host of today's session. This webinar is one of a series planned for 2022, and the attendees today will receive information on future presentations closer to the events. We trust that you find today's presentation entitled Geotechnical Solutions with Multiple Techniques both informative and enjoyable. Just a few items before we get started. All attendees are muted to avoid feedback and enable everyone to hear the presentation, but questions are welcome. Questions can be submitted through the chat window as shown on the slide and will be answered at the end of the presentation. Due to the large number of attendees, there will likely not be time to answer all the questions live, so unanswered questions will be answered in a follow-up email. Also, please note that this session is being recorded. Lastly, a 1-hour PDH credit is available for attending this session. Please respond to the poll at the end of the session to register for the credit. Now on to today's session. Today we have 2 presentations on interesting projects where multiple geotechnical construction techniques were applied to construct the optimal solution. I'd like to now introduce our first speaker for today. Andres Baquerizo is a vice president with Keller North America, working out of the Miami office. Andres joined Keller in 2002, following his early career with his family's consulting and construction company in Bogota, Colombia. He's a licensed professional engineer and has received numerous awards and recognitions, including the Miami Engineer of the Year and his appointment as the leader of the Keller Global Product Team for Continuous Flight Augers. I will now turn it over to Andres for the first presentation on the Aston Martin residences. It's all yours, Andres. Take it away.
Thank you very much, Jim. I'm going to share my screen now. Thank you for being here with us. I hope my audio is okay. Let me know if it's not. So talking about the Aston Martin's super interesting project, we have this new setup, right? 69 stories, up to 2-level basement that is going to be installed right next to the river in a really porous condition where it was backfilled back in the day. So that is not the traditional sand. It was backfilled direct from the river and created this new land with an old seawall to be installed. Pretty tall building, abutting buildings, super slender. Couple of things on the location, as you can see, right? It's kind of in Florida, Miami, downtown Miami, right next to the river, pretty close to kind of new construction happening in different places. Specifically, we see the site as it is, end up being a kind of a really narrow, stretched, triangular shape that is difficult access for kind of transportation, but more importantly, super slender with a river that has been dredged out for another 25 or so feet, creating, of course, an instability on the foundation. The slenderness of the building began to be a challenge. And so they contact Keller to start reviewing what could be done to create this beautiful project. When you see it from the perspective of the architect or the developer, it's a pristine location. It's the Miami Bay, right in the river entrance, right out down in downtown, tallest building, beautiful setup with a marina right in front of it. A couple of other kind of shots and 3-dimensional animations from the building. Nice pool right at the top of the project, right at that point, with nice views of the whole Miami and the upper kind of echelon of penthouses on the project. Those penthouses are worth between $45 to $60 million when they sold them. Right now, they're going for more than that. If they resell them right now, should be in the $85 million. So super high-end clients that can have a very interest in finishing the project on time. Now, when we transfer the view of the developer or the buyers to the view of an engineer, it changes the perspective, right? The perspective at that point you end up seeing is a pretty tall building, kind of slender in even the long direction, and even more slender in the short or narrow section of the building. It has only 3 points of contact on the base of it, and you can see it more or less in these blue lines coming into the model. With having a shear core in the middle with some massive kind of a transfer of that whole shear at this base, creating into these massive mega columns. Looking into that perspective, at that point, you see the load transfer coming down, then a transfer to those mega columns. And so you end up having 4 mega columns that has about 100,000 kips at each mega column. Tremendous load arriving to a place with a slender condition and a moment. And so the typical distribution of a foundation at that point, including a basement, will be tough, as there was not enough space in the area to put enough shaft casings. Even though the solution could be performed, the delay on the time on the schedule will be kind of drastic. Looking for other options of what to perform, we end up kind of proposing a different solution. Now, importantly, being right next to the river on a almost old seawall that is kind of having all kind of water protruding through it, it becomes concerning how to build, of course, the basement on that location. A little bit of the foundations as proposed, and we're going to talk a little bit more about them in a few. So we began to propose to seal the whole bottom with a soil mixing. We're going to talk about that in a second. But more importantly, we decided to go and try to implement a new technique called the tangent bearing elements. It's a name registered by Keller now, to support this slenderness of the columns to get all the vertical loads and be able to withstand these moments in line. As you can see, the piles are pretty close to each other, touching each other, which actually goes against what the typical code would allow. And we'll talk a little bit more of that in a couple of seconds. A drastic schedule doesn't seem as much, but when you're that close to the water with this 70-story building, on a 60-month schedule seems a little bit tight. But more importantly, the time to seal the bottom and the time to install all these tangent bearing elements end up being pretty tight to be able to excavate and complete the conditions. Keller proposed a lump sum in those 3 elements, right? The deep foundation, the piles, and the excavation, providing a complete water-dry excavation. It resulted in about 570 Tbes. We're going to see them in a second, how they're installed. Another view, you can see us already working on that site at that moment. And at the end of the project, it resulted with 7 different techniques or so, right? Permeation grouting to underpin the neighbors and the cell center, soil mixing to seal the whole bottom and prevent water migration, case-secant piles to allow the excavation to abut the neighboring building without undermining them, jet grouting to seal around obstructions. That area had an existing building before, and we found all the old shafts for the elevators and the pools that we had to deal with. Some tremie seals when they change the location of the tower cranes, and we have to reseal some areas right next to the water. Tangent bearing elements, bracing to reduce the flexion on the excavation, and of course the excavation and pile cutoff. A complete lump sum agreement to be able to provide a water controlled environment on the job site. As a view, you can see the whole bottom being sealed. We're going to talk about how we seal those bottoms. We put tangent soil mix walls around 3 of the sites, a case-secant pile in one of the sites that is touching the neighbor, and compaction grouting as permeation compaction grouting as underpinning to allow the neighbors to be safe and sound while we do our work. The elevations of the site was a total excavation. Can random here, it got cut off, but it's about the minus 20 foot NGVD from an existing grade of about 7, so the 27-foot excavation and the maximum excavation, which was close to those mega columns. As you can imagine, not that many companies in the world has the ability to have all those techniques with all the expertise to be able to execute them flawlessly. Our subsurface soils in downtown Miami end up ranging pretty similar in all these projects. An upper sand layer, an organic silt and peat, followed with limestone, and then intermediate of sand and cemented sand and limestone. The initial projects in downtown Miami were sitting here about 40 feet below. The second wave of buildings in the 1990s, early 2000s are here in the 70 to 90 feet depths. And then these new projects are sitting in between the 130 to 150 feet limestone layer to control the settlements of the building long-term and short-term. Couple of pictures of how we execute these techniques as we go through them. You end up seeing a KCFA. So a KCFA ends up being a casing that has an auger inside of it And so when the casing is rotating inside the ground, the auger takes the cupcake out of that casing through it and end up dropping the spoils through the chute. The nice thing about it is because when you're doing the installation of the casing, followed by the auger, the soils cannot migrate into the casing, and that creates a very good solution to be tied into neighbors. Before we did that, we did come in and did compaction grouting on that area. It doesn't seem much because it seems like a little just kind of a parapet wall, but reality is that is the valet entrance for all the restaurant and the club and the building and the hotel next door. So interrupting the valet area would have been a tremendous detriment to the neighbor, and you end up having all the Lamborghinis and all the Ferraris being parked on a daily basis in that area. After we did some of these case foundations, we end up proceeding, of course, with the soil mixing. We're going to talk about the process in a second. You can see the pictures here. Soil mix plant located away from the kind of basement. The basement occupies the whole property from the sales center all the way back to the neighbor with just one access road. We use crane mats to stabilize the soils, as working platform end up being one of the most critical aspects of any of this work. And we do have a quality control system on site where we take wet grabs and cure them for strength. We take then cores that we end up taking 7 days and 21 days after to also test them against the wet grabs to guarantee that the strength of the material and the permeability is what we're looking for. After that is, of course, followed by piles. These piles are pretty deep elements, full length reinforcing to allow for tension and compression. These specific piles, in this case Tbes, if they were treated individually, they could have withstand some of them up to 1,200 tons in compression and up to 600 tons in tension. The lateral loads are interesting because as you end up putting a bottom soil mix plug, you are improving the soils and that kind of locking the piles in position, and they increase the capacity laterally on that pile. So the concern at that point ended up being shear, but not the bending moment on the pile as being braced in his place. In a little animation, a little bit cartoonish, but it does perform the trick to show us where we are. We end up drilling down, pre-drilling the site to pre-mix the whole area and guarantee that it's a similar kind of soil. Nothing increased better quality than actually repetition. So once we have the similar soils, the drillers are going to be able to have the same feeling over and over again to guarantee that what they're doing is repetitive. At that point, we bring the soil mix tool. It's a big blender, 10-foot diameter, 9-foot diameter blender that shoots cement through the blades. I end up creating these circles of soil mix at the right elevation. It can be overlapped and it can change the elevations to follow the contour of the bottom of the excavation. We continue to put all the soil mixing on the bottom. We do the soil mixing on the bottom first and not the walls to make sure that the rainwater, when it comes in, it has a place to permeate as we're doing our work. The more soil mix we install, the more sealed this site becomes. And more even when we change the tool to a 3-foot diameter soil mix tool in a twin basis or in a triple axis, and end up installing I-beams that soldier and pile and lagging every 5 feet or so. So you end up having a soil mix connection to the bottom soil mixing and then reinforced with I-beams every so often. Once we have done this process, we have created a complete pool under the ground without excavation, but preventing the water migration and preventing kind of deep excavations. In the past, when we have attempted to do this with a tremie seal, we'll have to excavate to the bottom of the site underwater and then pour a tremie, which increases the depth of excavation and that increases the size of the beams. So this system braces the system to allow for some areas to be cantilever and the deep areas to be braced. The pile rig will arrive at that point and we begin to drill the piles and pour the piles through the soil mix, guaranteeing a nice porous kind of connection. As the auger cast piles are not cased, they end up creating a very rugged connection on it. Full-length steel installed in the different piles, and we add any anchors that we see fit for the buoyancy during construction. As during a certain point in time, the whole excavation will be ready with the water pushing upwards and no weight counteracting that upper pressure. When we finish the last set of piles, we'll get all the quality controls checked to make sure everything is jiving. And at that point, we get the internal Keller engineering department okay to proceed with the excavation. end up being a demolition excavation through those piles, and then we end up creating the detail excavation around the piles to make sure that they don't break, and we expose the rebar for connections. Pretty simple process, a lot more complex to implement in the right place. We have done about 30 of these in Miami, totaling about 1.8 million square feet of basements and excavating more than 2.5 million cubic yards in the last 10 years. Now, let's talk about a little bit about tangent bearing elements. So the issue with tangent bearing elements is like there's a story back in the day where somebody in many years ago in the 18th century make a new clock that was precise to the second for more than 100 days. This implies that no boat will get lost in the sea, and a lot of boats will have boated crashes against kind of the sea coast for many, many years. But the issue that he had is that its design was going against everything we have said was the best throughout history. So nobody was willing to challenge what we have done. Similarly, if you go and think about Tbes, we have these caissons or these lorry walls installed. We have the drilled uncased elements like the Arcas piles from CFAs. But if we merge them in the middle, there could be a TBE, which is how to create a caisson without casings, right? In a faster mode. We have found about 30% savings in time. So with that in mind, imagine a casing of that size, and if you replace it with 4 elements touching each other, it will create at the end of the day a similar area, surface area for friction, and a similar bottom area for end bearing. Similar for a kind of a barrette, and you replace it with a section like that. So the city told us, okay, if you're gonna do that, you have to prove it. And for that, we end up installing kind of a couple designs and presentations to the city that show that typically you have this behavior for piles when they are installed independently. But when you do the TBEs, of course, you're going to have a possible loss of the middle section of the friction. So how effective it could be. Now, in Miami limestone, the friction is so high that the losses could be less. And so we decided, let's prove it. With that, we contact Dr. Felenius about some of the settlements analysis and some of the conditions for them to be in line with typical engineering approaches. So we install a pile and we put kind of O-cells on the bottom to test a single pile. With that single pile, we came through and then installed 2 piles touching each other with 2 O-cells run simultaneously. And then we said, what happens if we put 4 touching each other? And then we end up installing them in a line and other ones in a square, and run all those O-cells simultaneously. All of them run simultaneously to prove if all of them could act and have the same capacity. After that, we end up testing laterally the 2 against the 4, and then we end up installing some sections to test a 4 TBE laterally and prove that it had enough lateral capacity. We end up getting a successful load test, and with that, we end up changing some of the ways that the solution is being done. Part of the equation is to be able to get all these massive loads in a smaller caps and be able to reduce the thickness of the pile caps for punching shear. This resulted in this kind of setup in the case where you have the tension end up being the black marks and the compression that being the clear ones. So pretty good clusters, but a really slender building that could be built. You can see us putting the tangent bearing elements. It's excavated at that point, how you began to see them, how they end up, right, in lines, peak lines. After pile chipping, we end up chipping the piles and excavating through the soil mixing and exposing the rebar for the connection in that behalf. And they end up proving to be super effective on that solution for the specific soils. An aerial picture of the site already dried after excavation against the intracoastal. Water management was super minor with less than 100 gallons a minute of intrusion through the process, so they can put their waterproofing and build their caps as they are. This should be a little tour. Let's see where we are. Seems that is not working the video. We'll see. There you go. See the guys working on the site right there, putting the rebar, going through it. All the water and boats pretty close by. Some bracing to take the deeper sections for kind of deflection and protecting the roads. So nice project, pretty close to the neighbors, and a good success. The other day, I was able to rent a boat with a couple of guys on the office and went there and took pictures from the river, how it looked out. I felt very proud of our team when they achieved such an amazing task in the time that we had allotted for. Some of the team members that helped us to do that, the Simone, NB5, Coastal General Contractor, and Revuelta, the architecture firm. And with that, I thank you for the time, and I'll pass it back to you, Jim.
Thank you, Andres. Very impressive project. And go ahead and moving along, I'll introduce our second speaker for today. Robert Schiermeyer is a senior project manager with Keller, and he works out of the Denver office. Robert joined Keller in 2009 after graduating with a master's in civil engineering from Colorado School of Mines. He's a licensed professional engineer in 9 Midwest states and focuses on design build projects, primarily on structural foundations and landsides. I will now turn it over to Robert for his presentation on the Sheridan Hillside stabilization. Take away, Robert.
Thank you, Jim. Let's get this. All right, so I'm going to talk about a landslide stabilization project we did out in northern Wyoming and Sheridan, Wyoming. For those that aren't familiar, it's near the Montana border. It's right off I-90. Here on the right, you can see it's kind of on the frontage road there for I-90 is the town of Sheridan. The landslide was right here in the downtown area. Specifically, it was between Big Goose Creek and the junior high school. The elevation difference between the high school and the creek is about 80 feet or so. And then this length here is about a quarter mile long. And so here's a couple of pictures of the landslide. This one here is facing north, and then here's the other half facing south. And again, the school is up here on the hill and then the creek down below. And some closer pictures here. Again, this is the south side, then going to the right, the middle area, and a little more to the right, the north area. You can see here, there's actually a wall built years ago that seemed to fix some of the issues. They still obviously had some very big issues here to the south. And again, this is the landslide area. It was a collaborative funding effort between numerous parties, some from the federal government, some local, along with the city of Sheridan itself and the school. So the city first started by developing a investigation design team. They knew they had a problem, but they didn't know what to build to fix it. And so the city of Sheridan enlisted help from Keller, along with CDG Engineers, a local engineering firm, who teamed up with Golder. And then Keller teamed up with Trihydro, a local water resources firm, Engineering Analytics, a geotech firm, West Plains Engineering, electrical firm out of Rapid City, and American Engineering Testing with a local office there in Sheridan, a geotech firm. So first off, we went about figuring out some boring locations to sample the soils and figure out what we're working with in the landslide. We were somewhat limited in our locations because it was difficult to actually get a boring right in the middle of the active landslide. We were able to go up on the hill and also down below near the creek, which gave us a pretty good idea of what we were working with. AET was the one who went out and did the sampling here. A couple pictures of doing the borings. For many of the locations, we actually did continuous sampling. So here's some of the boxes here you can see of the soil samples. Primarily, the soils were a few feet of overburden, kind of just clay, silty kind of material, and then quickly got into a claystone bedrock. You can see here that most of the samples are intact, kind of a clay material or bedrock material, and the ones that are fractured are bedrock that kind of broke apart. One thing to note here that I want to point out was the lignite/coal layer. What we think was going on was you had all this claystone bedrock, but coal layers between them run in water. And so it almost acted like ball bearings where one claystone block would slide on top of another claystone block. And then here's just a picture here of one of the outcroppings. And so we did a few cross sections here, 3 to kind of model the site. Most all this gray area is claystone. You probably can't read the text, but it's pretty much all bedrock's what we're working with. So we're pretty sure that that coal layer was the culprit for the landslide. We had kind of a block failure where a block of bedrock would slide on top of another block of bedrock. And again, because of all the running water running through that coal layer. And so we did a slope stability analysis. We came up with a factor safety right near 1, which is to be anticipated considering that the slope had failed and was potentially continuing to fail, which would be a factor safety 1. So that made sense. And then we went about looking at how we'd fix that, increase that factor safety up to say 1.3 or 1.5. I want to say we shot for 1.5 for the permanent case and 1.3 in some sort of ultimate loading scenario. So a lot of times the most economical way to fix a slide is if you can just lay everything back and flatten it out. We obviously didn't have enough real estate for that here. Again, the height was about 70 or 80 feet, and we found that a safe slope would be a 4-to-1. So if you want to slope back, say 80 feet, you'd need 320 feet horizontally, which we didn't have. So what we decided to do was build a couple of retaining walls that totaled 40 feet in height. Then the other 40 feet going up, we would lay back. And those retaining walls, what we considered were primarily these 4 different systems here. Soil nailing, for those that aren't familiar, are horizontal nails on about a 5x5 grid, 5-foot horizontal, 5-foot vertical grid that go back about the height of the wall. So if your wall is say 20 foot high, they'd be 20 or 30 feet long, and they're all connected by a shotcrete face. We also looked at anchors, which are sort of like high capacity nails, a little bit different, but usually they're a few hundred kips. And you can tie them into the facing of your choice, usually some kind of reinforced concrete. And then we also looked at soldier piles, which are kind of like large vertical drilled shafts, either reinforced with rebar or beams. And we also looked at rock baskets or gabions, which we kind of liked for the creek, because the landslide actually moved a bunch of material into the creek, which narrowed it. And so we were required to return the creek back to its original width. And so there's going to be quite a bit of dredging. We thought gabions would be a good way to reinforce the side banks. So ultimately, the solution we came up with is shown here in the photo to the left, where what we ended up doing was we did 2 20-foot tall walls and again, sloping the rest of it. So we kind of had a sloped here in the middle, kind of sloped here near the creek. Then we had a 20-foot tall soldier wall with anchors. And then up at the top, we had a 20-foot tall soil nail wall. What we ended up doing was the soil nailing was just for local stability. We just wanted to come up with a 20-foot height here. And so these soil nails actually don't affect the global landslide stability. All of that was done through these soldier piles and the anchors. A lot of times for landslides, you'll see a repair done with anchors and concrete blocks. And so we kind of want to do that here because that's a tried and true method for solving landslides. But what we also wanted to do was, since we knew this coal layer running water was an issue, we knew there was a coal layer down here, down low, where we weren't really sure if we had sliding down here or not. We for sure had it up here, but possibly down here too. So what we did is we had these soldier piles that we installed that went through the coal layer almost like shear keys. And then we also put in anchors that were several hundred kips each to impart a load into the slide here and maintain the toe stability. And then I didn't show it here, but the gabion baskets are actually along the creek. And then one other technique, not necessarily a retaining wall, but a landslide repair technique, is a horizontal drain. We had some drains go back up into the slope about 100, 150 feet, intercept these coal layers and try to draw the water out before the water could reach the hillside face. So in the construction team we had, Keller self-performed about half of the work and was responsible for the entire project. We're also responsible for delivering a performance warranty for the project to ensure they wouldn't have any landslides in the future. We worked with the local general contractor, JR Civil, some of the companies mentioned previously, along with Jensen Drilling and Boulderscape. Jensen Drilling primarily focuses on the horizontal drains to draw the water out, and Boulderscape focuses on shotcrete. So our first step was to do the soil nailing, help us start building some working benches. The pictures here are not from the project. This was from the Cowboy Stadium when we constructed that. But I just kind of want to give you an idea of what you'd be seeing in the coming slides for pictures from the actual construction project, where you come down in about a 5-foot lift, install a row of nails, and then go down and do the next lift and the next lift till you reach the bottom of the wall. So here's a couple of pictures of the breaking ground at the top of the landslide, build our working benches, and then coming in and doing a row of nails. You can see here the grout coming out of the holes, and then the bar itself had quite a bit of corrosion protection. You can see kind of the epoxy coating here, but they also had a corrugated pipe in the ground that you can't see for double corrosion protection. Here's just applying the shotcrete. One thing to mention here is most people think of shotcrete with an operator kind of holding the nozzle by hand. We actually used a Mini-X for most of the work, just because of the volume and the quantities. We felt like this was better for safety, and you don't have the fatigue factor with manual operation. Then some pictures here of doing the second row of nails. Over here, I just want to draw the attention to the black tarp here. This is the drain board put behind the shotcrete. Again, we believe water was the primary culprit of the landslide. So we wanted to draw out as much water as we could. And with the horizontal drains, we draw the water out, but then we also put in this drain board for any water that might make it to the backside of the wall. Here's kind of an overall picture you can see here, constructing the second row of the soil nail. And what this allowed us to do was, if you recall some of the original pictures, it was a pretty jagged site with the landslide. By starting the soil nail wall first, we were able to take a bunch of the soil, push it down slope, and create some very good working benches. And so here's just going down to the third row. We actually ended up hitting an old landfill, dug up an old car, interestingly enough, but that was just a small area. We come to find out was an old landfill area that was not known prior because we missed it with the borings, but there was a small area, I guess, that used to be a dump site. And then here's just going on with the third row of nails. Again, the third row. And then the fourth row here was the last row. So we're getting close here to the bottom of the soil nail wall. We also did some testing of the nails to confirm the capacity. Just a picture here of that, running a jack to pull on them and measure deflection and make sure they're achieving the capacities that were in the design documents. And so here's a picture of the completed wall, about 20 foot tall, 4 rows of nails. Once we got this done, then we're ready to go to the next wall, the soldier pile wall with anchors, working our way down the slope. Again, just to remind you of the design, the soil nail wall here was the blue line. Now the red line here is the anchored soldier pile wall. This green line here is actually the edge of a maintenance path that we'll install to help maintain the drains. These drains that help draw the water out, they do need to be flushed periodically, so every 6 months to a year, to keep them flowing properly and not getting plugged. And so this green to red line just kind of shows the width of a pathway that'll be constructed for maintaining that. But the red line here is the soldier pile wall. Just a few details from the drawings. I'd like to draw your attention, if you can kind of see here at the bottom left, it's about a 36-inch shaft. And then what we did is we did 2 wide flange beams, W sections. And so here's the fabrication of them. You can see the 2 wide flanges. And the gap here in the middle is for the anchors. Sometimes when people do anchors, they put them like offset to 1 beam, but we prefer to do 2 beams, put an anchor right through the middle. And then here's just a picture of the installation of it. You can see them drilling the hole. You can also see one of the previously installed soldier piles here to the left. And here on the right, you can see us bring the soldier piles down to the work area. And then here's just a few of them installed in a row. They're on about 10-foot centers. Once we got the beams installed, then we did put it in lagging here to span between. We'd eventually cover this with the shotcrete face, but we'd start with the wood boards initially. And again, if you look behind it, you look at this and you're like, wow, this doesn't look like the landslide material from the pictures before. That's because most of this is bedrock material, but it's more sort of a block failure where it was sliding on the coal that was running the water. And again, just kind of an overview picture down here are the soldier piles in the previous pictures. And again, the soil nail wall here is about 20 foot tall that we completed previously. Again, like the soil nail wall, the drain board here to help collect any water that might make its way to the wall face. And then just some pictures here of the anchor installation. These anchors were about, I want to say 100, 150 foot deep. They varied in length and a relatively steep angle. What we wanted to do was actually get down below any possible shifting or moving landslide material. So we installed these a little bit steeper than typically to make sure we got down to a nice competent material. And then here's the connection, pretty stout. The reason for this is these anchors were a couple hundred kips. So we wanted to make sure we didn't cause any of these wide flange beams to yield and distribute the load properly. And then here you can see that coal layer we got down to that was running the water. And you might think, well, look at this, this looks pretty dry. Where's the running water? Well, we get here and a little bit deeper and it started running out. And this is all from this coal layer kind of collecting down here. We did the anchors. We actually used regrout tubes. For those who aren't familiar, this is a very nice insurance policy to put on your anchors. When you install anchors, you stress 100% of them. And so if you have even a single failure, you have to come back and install a replacement. So what we like to do is put in regrout tubes. So if you do happen to have any failures, you can come back in under high pressure, frack the grout, inject more grout and increase your skin friction, your bonding. So we put these in quite a few of the anchors in an area where we were worried that we might not get the bond we needed. So here's the first row, and if you look closely, you'll see a large jack for stressing these. As I mentioned, you stress 100% of the anchors. Just here's a picture of them all stressed and locked off and excavated in the second row. Again, you can kind of see the coal layer down here where it gets a little darker. And again, putting up all the lagging boards. And the coal layer again here. Again, this is what we think is the primary culprit for the landslide. And then again, all the water that runs through it. So the next thing I was going to show was the gaping wall, or the rock basket wall for the creek widening. And one thing to mention here with the creek widening, when we're doing the excavation to clear out and dredge out the creek, we actually discovered some old stone columns here in the pictures. Full disclaimer, this was not Keller. This was a previous repair that was attempted. The thought was to do kind of a ground improvement to increase the shear strength of the possible landslide material. But what ended up happening was ended up just kind of having a block failure. So we found those when we were dredging out here to construct the rock basket wall. Initially, we put a basket down below grade for scour, and then we built the baskets up. One thing to mention is gaping baskets or rock baskets are usually gravity wall. They kind of look like a pyramid, and just the self-weight is how they act as a retaining wall. But we actually did something unique here, where I don't think a lot of companies do, where we actually put in soil nails or anchors tied into the rock basket wall. So instead of relying only on the self-gravity weight, you can see here a soil nail or an anchor kind of poking through. We actually put in dividers here. And here's just another picture of the nail and the rebar here before we pour our concrete. And we actually end up tying those nails into the concrete, which are tied into the rock baskets. We think that offers a much better product than just the self-weight of the rock baskets themselves. So depending on the height of the baskets here, we either did 1 or 2 row of nails / anchors here for these rock baskets, but something kind of unique you won't see every day. And again, just a picture of the creek widened out here with, I think it's about 4 rows of rock baskets for this north side, or I guess you can count it here, maybe it's 5 or 6. And then here's the soldier pile kind of working its way to the north. And again, just to remind you of the design kind of overlaid here, you can see the blue line is the soil nail wall, the red line, the anchored soldier pile wall, kind of coming along here. And then we're going to start working on the gabings here to the south soon. And then here's a picture going back up to the soil nail wall. So originally when I mentioned we finished it, we had just installed the shotcrete and the nails. We didn't make it look nice or put a structural face on it. And so here's a picture of us cover up all the nail heads and all the connections. This is our initial face, and then we'll later do an architectural finish that's carved and stained. And again, just another picture of this shotcrete covering up all the anchor connections or the nail connections for the soil nail wall. And then here was the architectural finish I'd mentioned, where we applied another layer of shotcrete and carved and stained it. This is the initial carving phase, trying to make it look like a natural rock outcropping as opposed to just a concrete wall. Just another picture of carving it. You see here way in the background the carving. You can also see the gaping wall in the creek, then the anchored soldier pile wall. Just another picture where you can kind of see the entire wall here, the bottom lower wall and the upper soil nail wall. Then here's the staining. I picked kind of a brownish color, try to make it look like kind of a sandstone deposit, kind of a natural rock. And again, here's just another picture once we finish the staining. And then we're doing the same thing for the anchored soldier pile wall. Once we got all the anchors in and tested, locked off on the lagging end, we're going to do a reinforced shotcrete face there too, just as like the soil nail wall. Just a close-up of how much rebar we put in this wall. I want to make sure that if there was another landslide, that the loads could span between the soldier piles. And then the drain insulation I mentioned, where we did horizontal drains to try to draw the water out of that coal seam. So this is the rig that Jensen Drilling used to construct those horizontal drains. They drilled back about 150 feet. Again, they actually drilled uphill to try to intercept those coal seams. And here's the design again, just from before, where we're drilling from down here, we're drilling up to try to intercept the coal seam. And it was about a 4-inch hole, I want to say, with a perforated pipe. And then that perforated pipe would collect the water and come out the face. And again, these need to be maintained and flushed periodically, say every 6 months or a year to keep them flowing. Otherwise, they can get plugged up. So here's a picture after the drains were installed. You can see all the groundwater we grabbed from the coal seam and brought through the face. I guess we didn't plan ahead very well for this, but the final design did include funneling all the water into a PVC pipe drain system. And so here's a picture of where we funneled it all into the pipes, into the drain system, and this guy was pretty happy when we got this all cleaned up. And then here's just a picture of all the drains poking out, access to clean them out periodically, along with some of the shotcrete face being complete. Then here's a picture from the south side looking north. You can kind of see the gabion wall here on the south side complete, all the rebar up for the shoulder pile wall. And then winter started coming in. We started this project back in about May or June at the start of after the winter season. And then the goal was to get everything stabilized from a future landslide during a potential spring runoff in 1 year. And so the goal was to get all the walls built and stabilized prior to deboning for a winter break. And that's how it looked pretty quickly. I think this was taken in October up there in Wyoming. Well, we needed back to work because we weren't quite done yet. So you can see here, still stressing anchors, trying to make sure everything's done before the winter hiatus. Also before the winter hiatus, we had all the visitors from the funding agencies show up. Unfortunately, they picked a day after all the snow melted, so it's pretty muddy, but coming out to inspect the progress. You can see here, we're pretty close. We did the gabion wall to the south to widen the creek and to the north, and then we just have this little bit left here to pull out. Once we got that done, we had a good spot for the winter break. We got our soil wall done. We got all the soldier piles in. We got all the anchors in. We got all the gabions in. We're going to take a break in winter. Then we came back the next year, starting to finish up the shotcrete. Came back sometime in April, I believe. And then same thing like the shotcrete wall, carving it to look like a natural rock outcropping. Although maybe we remobilized a little bit early. Snowstorm actually hit us for a week or two. But then after that, we got back to carving it. And then here's the finished wall. And the next step was to do that maintenance path I mentioned for the drains to make sure you can flush the drains. So here's the start of the maintenance path. And here's one of the large pipes. I showed those pipes earlier for the water. There's actually quite a bit more that I haven't shown any pictures here, but funnels into a massive drainage system to try to funnel the water out of the hillside. And again, the pathway here, and along with some riprap between the creek and the pathway. Here's kind of a nice little picture showing the creek, the gabion, the rock basket wall, the riprap, along with the pathway and the two walls. You also see an MSE wall here. That was to help just get some grade gain here for make a flat pathway. Here's the pictures. We're getting close, about halfway along with the path. And then here's a drone photo of the entire project. You can see the two walls here. You can see the pathway getting close, a little over halfway done. And again, just working our way to the north, putting down the road base, and then pouring the concrete. And also it's a little bit of cleanup. So doing some cleanup, you can see the hydro seat up here. And then spray washing, getting everything cleaned up. And then I mentioned previously the performance warranty. So one of the things the city was worried about is there was a previous picture when we started installing the gabion baskets that you see the ground improvement that didn't work so well the previous time for a smaller area of the project. And so this time they wanted to make sure they didn't do something that didn't work. And so what they did is they had us provide a performance warranty where we did as-built and had to warranty against any future movement. And if there would be future movement, then we'd have to come out and repair for free. So as part of that, we went around the walls and installed a bunch of survey benchmarks that did as-built so they could monitor for movement over time. So we had point shot at the top and bottom of every wall on, it might have been about 50-foot centers. Then here's a couple pictures of the completed projects, just a reminder of where we started and where we finished. The locals in Sheridan affectionately call it the Great Wall of Sheridan, which is kind of cool, I think. And so very cool project. And here's actually a picture that one of the locals sent me a couple months ago with all the grass grown in. And we completed this project about a year or 2 years ago. So, and just a special thanks to everybody involved. And there was actually, it was very nice. A bunch of local companies were actually able to help construct the project, which was cool. And Jim, give it back to you.
Okay, thank you. Let's see. Oh, didn't turn my camera on. There we go. That was an interesting project. Thank you, Robert. Quite challenging. Being located in Florida, I'm not sure what all that white stuff was on the ground, but I believe you. As a reminder to our attendees, and we had a couple of chat questions about it, there's a 1 hour PDH credit is available for this session. So please respond to the poll that you're going to see at the end of the session here. It should be on your screen. Let me see. I guess you'll put it up there, Lauren. And then we have a few minutes for questions. Very good. So let's see what we've got here. Let's see. I'll go back and forth between the two of you and give each a break. First one for Andres. It says, "What are the benefits of TBEs?" So Andres, let you take that one.
So a direct benefit of the TBE is the ability to take the loads of the column, and be transferred directly into the elements, avoiding having to have a punching shear effect or bridging the cap. That means thinner pile cap, and that means shallower excavations. So it's a way to take those loads and thin the pile caps and expedite the excavations and minimize the watering concerns.
Good. All right, Robert, here's one. Was any strength testing performed on the claystone / coal bed layers?
Yes, I believe they did direct shear testing on it. Unfortunately, I don't have the slide handy, but I believe they did do some strength testing on the claystone. And so they actually end up classifying the claystone in 2 separate types, weathered and unweathered, based upon those strength results.
Good deal. Thank you, Robert. And here's one, go back to Andres. What is the maximum depth of basements that can be built with the deep soil mixing method?
An interesting question. That has a challenge that has been brought up quite a few times. Right now, as we stand, we feel comfortable with a 60 feet depth total excavation. Of course, that will require a lot of bracing or tiebacks to support the walls for deflections or moments. But the accuracy of the soil mixing process with a 60-foot that is about a 4 to 5 story basement is the maximum that for now we feel comfortable with.
Very good. And we'll jump back over to Robert. Question was this a design build project?
No. It was actually design bid build. We were involved in both parts of it. But what it was is the city wanted to make sure they had sort of a landslide expert on the design side of the project. There was a concern because they had a lot of mixed feelings about the previous time when they tried to do a little bit of ground improvement stuff. And so they this time they wanted to have a bunch of parties involved, I guess, on the front end to design it. And then the construction ultimately went out to bid as a public bid.
Very good. And Andres, what is the expected water intrusion into the excavation? And kind of question along with that is, do we need wells to dewater?
Great question. Yeah, the when we're doing the soil mixing process that are gonna be really watertight, the permeation design is based on about 0.005 gallons per minute per square foot. It all translates in a basement to about less than 200 gallons a minute. But reality is that we have experienced less than 50. So it's super watertight. Our concern in the being is rainwater. So once you create these massive 40,000 square foot or 80,000 square foot excavations, when it rains, you can collect easily 40,000 gallons in a rain event. So you will need wells to take the water and dispose the water that you collect through a rain. So rain events are more concerning than the water that is going to follow. An easy 4-inch electrical pump can handle any water intrusion, but you should be ready for at least 2 6-inch pumps to manage the rainwater and get it out of the site when it does.
Good point. And so the second part of that question was, do we need wells for dewatering at all?
So yes, in the sense of, not as an obligation, but in some cities like in Miami, you have to be by law, you have to, by regulation and law, you have to actually re-inject any water that it's collected or it permeates through the system. So in Miami, you do. There are some other areas you probably can dispose in a retention pond, but you have to be ready to have a place to dispose rainwater in heavy doses.
Good deal. Robert, how long were the soil nails connected to the gabions? And how far, how long, and how far did you install the nails along the gable wall? I guess that's along the length of it.
Sure.
So how long? And yep, go ahead.
If I recall, they were 20 to 30 feet, I want to say, and we actually designed them like an anchor. So those familiar with anchors, we actually did a PVC sleeve unbonded length for the upper 10 or 15 feet of it, and then had a lower like 10 or 15 foot bond. And so I want to say they're about 25, 30 feet. And they were actually designed more like anchors, but we didn't pre-tension them though. So I guess in that sense, they're like a passive soil nail element. I hope that answers the question.
I think that sounds pretty good. And Andres, I got a question. How deep can we apply chemical grout between the project and the existing buildings? Maybe that's how deep did you install it?
And in this specific project, what our intent was to make sure that any connection between the existing building or foundations to the limestone layer was uniform. So it was not deeper than 25 feet. We have done it deeper than that, all the way to 50, and could be more. But in general, when you're underpinning and permeation grouting these buildings, what you're trying to do is get to that level of support that will get you to a solid sandstone, cemented sand, clay, or so, and take the effects of this loose sands, cohesionless soils out of the picture.
Very good. And Robert, why timber lagging and not concrete was the question.
Oh, kind of why the redundancy?
Or I guess they said instead of concrete, but you did both with the timber temporary and then the concrete in front. But
yeah, so in front it was actually I want to say it was 12 inches thick, double mat in front. So the final face was fairly robust concrete face in essence. Now you might have the question of why would you put up the wood boards and do the shotcrete? Normally you see kind of one or the other, and so logic would say, well, get rid of the wood boards, just start with the concrete. That was kind of a constructability call, I think. Just wanted to make sure that if we had to do any kind of fill in some of those areas where you saw when we're building the benches, I think there was kind of a bit of a gap behind the wall. So what we decided to do was, instead of messing with two-sided forming for concrete or things like that, we wanted to make sure the wood boards were up, and then we could backfill as needed. And I guess we felt like the cost and the schedule to put up wood boards wasn't significant, but it would have significant help with the constructability of the final shotcrete face there.
Okay. And another one that came in here, it says the final product looks beautiful, but wondering why the solution involved 4 retaining methods. Gabion, soldier pond, lagging, soil nails, and I think you mentioned MSE wall. So can you touch on the selection, reasons for the selections there?
Sure. So we felt like the kind of the anchors and soldier piles was the most robust wall, provide the most resistance to a future landslide, but it's also the most expensive. And so we tried to use some lower cost options where we could. So the soil nail wall, I might have mentioned, doesn't really provide global stability. It simply gives us a 20-foot vertical wall. And so we liked that because we felt like that was a lower cost wall to at least get us that vertical height we needed. And then in the creek, we ended up using the gabions. Twofold. For scour, we liked them a lot better than some sort of concrete wall. We prefer the rock baskets. It's a very common technique in the streams. We also like the aesthetics of it. We thought it looked nice because a lot of creeks have riprap, and the rock baskets kind of look like riprap. And so aesthetically, they like that. And then cost-wise, I want to say that was the lowest cost wall. The MSE wall, what that had to do with was we potentially, because that wall was only about 3 or 4 feet tall. So another way of doing it would have been to make the anchor soldier pile wall 3 or 4 feet taller, and then we wouldn't have needed the MSE wall. But the city actually mentioned they didn't want any walls to be higher than 20 feet vertically. Aesthetically, they want to kind of cap it at 20 feet. And so what we did was we decided that an MSE wall is a quick and easy way to do a 3 or 4 foot tall wall, just these gravity blocks. And then it also make a nice good base, dumping a bunch of road base in there for the maintenance path. Because the maintenance path, I didn't show a picture, but the equipment for flushing the drains is actually a very large piece of equipment, almost like a fire truck, if you want to think of it that way. And so the road needed to be fairly robust. It wasn't just like a thin 4-inch sidewalk. It's a fairly robust, almost like a road, so that this fire truck type machine could drive on it.
Good deal. Thank you. And I think this one's for Andres. What is TSM?
Thank you for the question. We referenced as a twin soil mix and now a triple axis soil mix. So it's the same TSM. end up being two blades rotating simultaneously, kind of against each other, overlapping, creating like a little 8 or an infinity shape to begin to create a secant pile. So instead of installing one at a time, you can install 2 or 3 sets at the same time. In this case, for soil mixing, which end up being about a 200 to 500 psi strength wall reinforced with I-beams as soldier piles.
Very good. And another question here for you, Andres, is how did you handle tolerances on TBE locations?
And that's one of the reasons on the presentation we said that is perfect to be utilized and installed in specific soils. You do need the upper soils to be pretty stiff. You may need to, in some jobs where we have done, excavate and replace with flowable fill. So when you're drilling, it maintains the first area so it doesn't start to wobble the auger around. We do, in these cases, install the piles. We will have a surveyor that is going to be shooting the stem of the auger in one direction and another surveyor shooting the stem in the other direction to make sure that when it's going down, it will stay plumb and not bite into the previous pile. The reality is that the strength of the grout that we're using, being that 8 or 9,000 psi, is a lot stronger than limestone or sand. So the auger will always try to follow the path of less resistance. Our concern is not biting into previous one, it's actually diverting too much. So that's what we do. And all the stems are thicker than typical, and they end up being welded in the interlocks instead of just connected to prevent the little kind of wobbling of the auger percent to make it stiffer.
Very good. And here's a cost question for you, Robert. What was the final cost of the repaired wall?
I think all into the city when they cover, in design, inspections, construction, everything. I think they told me it was about 10 million. Which, look at the final price, seems like a bargain to me, but I think that's about what they spent, I think.
Good. And another question, follow up on the wall. How did the project interface with the older existing wall? Was it replaced or did you tie into it? Did that make sense, Robert?
Oh, sorry. Yes. How do we do the? So I saw that come through. So let me share my screen real quick. I'm going to show a picture here. So kind of zoomed in here. So in the upper right, this was the existing wall. And then our new solar wall was here to the left. And so I think the question is, how do we tie into that?
Mm-hmm.
So that's an interesting question that came up because there was a liability concern with this performance warranty where if we tie into it or undermine it, are we now taking performance liability of the existing wall? So what we actually did here was the existing wall actually kind of sloped up to the existing grade there. And what we did is we started up here and then sloped it down. So this soil wall is only about 5 feet tall up here. And then down here is where it's 20 feet tall. And what we did was we actually built a middle wall, which I didn't really talk about here, to kind of bridge that gap, if that makes sense. So we didn't really structurally connect to the existing wall. All we did was we actually just stained it to match our walls. Originally, it was a gray concrete color, and we stained it. But what we did is we built this small little wall in the middle to kind of bridge between the two, if that makes sense.
Good deal. And another question along with the landslide says, has there been any monitoring of the stream banks downstream from the gabion basket installation to see if there's any increase in stream bank erosion in the unarmored stream banks?
I'm not sure. I know the city called me and asked me about if they could put boulders in the creek because I guess fish like to lay their eggs around rocks and boulders. And so they're curious if they put boulders in the creek, that might affect some of the scour. I know originally when we were doing this, the design for this, they ran all their HEC-RAS models. And one of the issues was originally when the landslide material flowed into the creek, the narrow creek increased the velocity. And they wanted to increase the width, the base of it to 40 feet, which we did, which lowered the velocity. Has anybody gone there and inspected to make sure they're not undermining or scouring the rock baskets? I'm not sure about that. When I was out there a couple of months ago, it all looked good. And then the other side of the bank, where all they have is just riprap. I know they have a whole project with that. I forget who's funding that one, but rebuilding the other side of the creek bank. And most of the scour, from what I understand, is up along our side because of how the water hits it, if that makes sense, we're the outer bank. But I guess I'm not sure. I guess the answer to it is I don't know of any exact monitoring they've done or not for the scour.
Good deal. Thank you. And we're out of time now. So any unanswered questions will be addressed in a follow-up email. And you can contact either of the speakers. We had their email address shown earlier. And if you didn't catch it, go ahead. You can also look through LinkedIn. You can find either one of them. So thank you for attending, and we hope you enjoyed and benefited from today's webinar. Stay safe. Bye, everybody.